Hey everyone, this is the next lesson in the exponential unit. We looked at exponent laws yesterday, or results from when you multiply powers and so on. And then this is kind of an extension of that, but it just gives you more time to practice each of the skills. So we're looking at kind of weirder exponents now, where you have zero and negative exponents. And we'll do the same thing. We'll look at number logic to try and help see that the results we're saying are true, or the rules or whatever, that they're true. Okay, so let's do this. We'll have a 2 times a 2 at the top, and a 2 times a 2 times a 2. 5 of them in the bottom. And so if you're analyzing that, you could say, okay, well, 2 divided by 2 is a 1, 2 divided by 2 is a 1. So people just say they cancel out. A lot of people would just jump right to this final line. I'm going to show you that we'd have really a 1 times a 1 in the top, and we'd have the 2 times the 2 times the 2 in the bottom. So, but again, people might just jump right to this. And then certainly the final result ends up being 1 over 2 cubed. Right, so we can look at this, 1 over 2, 1 over 2 cubed, right? And so I want to look at this multiple ways. And so we're also going to look at the rule that we know for this, right? We know from yesterday that a to the n over a to the m, any letters you want really, but like bases of a's, and then some letters in the top, we know that they are equal to n take away m. So that means that numerically, this one would be equal to, let me just do it over here maybe. So we know this is true. I don't know where to do it here for organization. We'll do it down here. So we'll say, so this thing is equal to then, I'll make some room here for this. So we know that stuff from yesterday. Undeniable logic that we've seen, right? So we end up with this 2 to the 2 divided by 2 to the 5 is equal to 2 to the 2 take away 5. Means, if we want to just space this out a little bit, right? So it's equal to the 2 to the 2 take away 5. So it is equal to 2 to the negative 3. All right, so just give myself some space here from this next one. But that's the kind of the result that we're seeing, that we ended up with, right? So 2 to the negative 3 is the same as 1 over 2 to the positive 3. So notice that the negative switches to be a positive, and you just sort of flip it upside down. Okay, so you flip it upside down, make it be a positive exponent, and those things are equivalent. Okay, so that's the negative exponent rule here. We have a to the negative n equals 1 over a to the positive n, right? So we've got a negative here and an understood positive here. Okay. So just want to move the zero exponent one to the next page, so I can clarify something that's kind of, make sure you recognize something that's kind of weird about this, right? So, I hope you recognize that this is kind of weird, right? So let's compare meanings here. So if you look at something like 2 to the power of 3, 2 to the power of 3 means that 2 multiplies on itself, right, 3 times. In other words, it equals 2 times 2 times 2, right? So it would equal 8. So that's what it is, right? Versus this new thing we're seeing is 2 to the power of negative 3, right? We know that it means, so 2 to the power of negative 3. Skip over here to the numbers. We know it means 1 over 2 cubed, which means 1 over 8. The weird part is, the really weird part anyways, is that in-between step. Right? If we're comparing meanings here, what the heck does this mean, right? So I don't know, do something like this, question marks, right? What does it mean to have 2 multiplying on itself negative 3 times, right? So I suppose I could do this without the exclamation points. I could, so ditto here means 2 multiplies onto itself negative 3 times. And that's where the question marks really are, right? This negative 3 times business. How do you multiply something on itself negative 3 times? Just doesn't make sense. Like the description. So I find that odd, that the wordy description of the exponents makes so much sense in the positive case, but and the numbers make sense in both of them, the positive and negative case. But the description is very odd. Okay, and the weirdness continues here. So let's look at the 0 exponent. So if we look at this case, the numbers would be 2 times 2 times 2, and 2 times 2 times 2. And so really all of those things, you could think of it as they all cancel out and you end up with a 1 times a 1 times a 1, which clearly is just going to be an answer of 1. Another way to think of this would be do this. So another way to think of this would be, or you'd have it equal to really 8 over 8, which of course also equals 1. So no matter what, we're seeing that it equals 1 as an answer. So if we compare this to what we know, again, the rule of a to the n over a to the m equals a to the n minus m. So that means that this thing would be equal to 2 to the 3 take away 3. So it's really 2 to the 0. I don't need as much space this time, so let me move that up. So there we go. So that equals that. So this equals 2 to the power of 0. And so that right there is what we're noticing, is that 2 to the power of 0, or obviously you could extend this to any number, anything to the power of 0 equals 1. Okay, that's just has to be true. It's the number logic shows that anything to the power of 0 is 1 that we just mapped out here, right? So again, the meanings of this, if we had 2 to the power of 3 like we did last time, means 2 multiplies on itself 3 times. Because we just did that on the other slide, but it makes sense. It means 2 times 2 times 2, so equals 8. Everything makes sense. Versus now, if we have this 2 to the power of 0, we're saying the logic shows very clearly that the answer must be a 1. But in the middle here, we have it means 2 multiplies on itself 0 times. And that just doesn't really mean anything, right? So again, how do you multiply something on itself 0 times? And why the heck would the answer be 1 from that definition? It just doesn't follow, right? It doesn't compute, whatever makes sense. So we just have to rely on the number logic that we see in front of us and go with it. Textbooks will refer to anything to the power of 0 as being quote unquote defined as 1. I prefer just to think of it as it has to be 1. Like the number logic shows that it's a 1. It's not that it's defined that way on purpose to make life make sense or anything. It's actually more that the numbers in life make sense. And so this logic that we just did right here, all that stuff, shows that anything to the power of 0 just is 1. Okay? So I don't think we need that page anymore. I'll get rid of that. And so the rational exponent stuff, I'm just going to show this one. It's not one that we can do as much with a number logic analysis. What I'm going to show you is, just to try and help you see which is which here, when we have, that one's from there, when we have a rational exponent, so a fraction in the exponent. The part that's in the top, the power of n business, that's kind of like normal stuff. Right? So if I'm saying a to the power of n, so a to the power of n would just be normal stuff. It would just mean a times a times a times a. There'd be n of these things. Whereas the over m, we haven't ever looked at that, right? So that's the new one. The over m part right here is the weirder part, and it's root of m. So if you just have a 1 over m, it's just root of m. If you have an over m with another letter, like n or whatever, then the m is, of course, the root part, and the n is the normal power part, right? So I'm going to get the color coding out through the rest of it here, but yeah. So I definitely remember as a student trying to remember which was which when I have a to the, in this case here of 8 to the 5 over 3. I definitely remember, having to try to look up which one was which. But remember, this part down here, right, is the weird part. So if you're thinking of that, you're like, okay, well, that means we have a cubed root. It's the new one. It's the weird one. And we'll talk about what cubed root means. So I'll come back to that one, but I just wanted to establish that connection there. So again, here, this isn't 16 to the power 2, of course. It's the weird one. It's the root of 16, right? So let's do this. We'll say, okay, it's square root of 16. And I want to just jump back to these easy ones because it's based, we'll look at stuff we kind of already know and extend it to unfamiliar things like what cubed root means. So of course we know that square root means you're asking a calculator if you're doing it, or you're just thinking about the logic of it, but it's some number times itself that we want to know, right? We want to know the number. We're saying some number times itself gives 16. And so obviously we could work backwards for this one because it's easy and just say, well, it's obviously 4 times 4, right? And so if you do square root of 16, it gives 4 as an answer because 4 times 4 is 16, right? So we get a 4 as an answer. Similarly here, we're looking for the square root of 25. Then we're just asking, okay, what number times itself gives 25? And the answer is 5. 5 times 5 is 25. 4 times 4 is 16. So this one's less familiar to us, I know, but we can probably figure it out, right? So basically we're saying, let's do one in between. Let's make this one our last one. We can extend to it. Let's add one in between here where we're just doing 8 to the 1/3. So that way it's a little easier to go through here. So cubed root of 8. So square root means what number times itself twice. Then this one's going to mean what number times itself 3 times. Okay, so this means unknown. What's the number that when you multiply it on itself 3 times, it gives you 8 as an answer. And so again, that's another one of those ones where it's a pretty easy example, right? You can look backwards and say, okay, well, it would be 2 times 2 times 2, right? So that answer would just be 2, right? So the final question here to look at that uses both parts is we have an 8 to the power of 5, like normal stuff, right? So that's normal. So we have an 8 to the power of 5, which is just normal stuff. But then there's also this cubed root. So you have to sort of combine both parts here. Okay, so that means that bedmass-wise, we just do what's inside of the bracket. Technically, you think of a root as a bracket. It's like root of all of this stuff, right? So bedmass would say just to do that exponent first. So let's do 8 to the power of 5. 8 to the power of 5 gives 32,768. I'll keep the green so we can know exactly where that came from. Double check that number, 32768. And then we have the cubed root of that. Okay, so if we do that on a calculator, it's going to spit out the answer that, it's going to spit out the number that if we multiply it on itself 3 times, we'll get 32,768. So you could certainly try you can just guess some numbers, like what about 15 times 15 times 15? And you're like, oh, it needs to be way bigger. Let's try 30 times 30 times 30. And we're getting closer. Let's try 35 times 35 times 35. And we're like, oh, too big. And so 34 times 34 times 34. Oh, still too big. 33 times 33 times 33. Ooh, just too big. 32 times 32 times 32. So as long as it's a whole number, it's something you could guess pretty easily, right? That's just what it means, right? So we're saying what number multiplied on itself equals 3, 2, 7, 6, 8. And by guessing and checking, you could get that it's 32. And that just shows, like, doing that shows that you understand what it means, versus if you're just punching the number into a calculator, you don't necessarily know the meaning of what you're doing, right? So by guess and check, you can see that's true. This calculator, some calculators can do this, some can't. So this one, oh, I know what we could do. Yeah, we can do it with this one. So some calculators would have like a special button where it would have like the nth root. So you could say root and then pick the 3 as the number. But this calculator doesn't. But that's why we have this knowledge about how this is really the same as, this is really the same as 3, 2, 7, 6, 8, the power of 1/3, right? So if I do 3, 2, 7, 6, 8 to the power of 1/3, if I can make this happen here, 3, 2, 7, 6, 8, and I'm just going to do the power of, and I'm going to just do 1/3 as a decimal with a bunch of numbers. So 0.3333 is what you get when you do 1 divided by 3. So you do a bunch of numbers, and it says, okay, so the number is, a very similar number of decimals there. It's 32 to the similar number of decimals as close as possible. Wondering if I can do that with this calculator, where I do 32 to the 1 divided by 3. I don't know if it's going to, it's not doing the right order of things there that I want. It's not doing the order that I want. So if I did, so I don't, I think there's a way to do this. So if I do 1 divided by 3, at that number, I hit M plus. So I've stored that into memory. And then I'm saying 3, 2, 7, 6, 8 to the power of memory recall. And now it's going to spit out 32 exactly, because I've asked it to do it to the power of 1/3 exactly. Okay. So the other way to communicate that, some calculators are a little bit better at doing trickier things like that. So this calculator would be good because I can do 3, 2, 7, 6, 8, and I can say to the power of, which is this button right here that I'm hitting a bunch of times just for emphasis. So let me go back and delete a bunch of those. And so we can say to the power of, and put it in brackets so that the exponent division happens first, and then gets operated on. So that'll give 32 exactly again as well. Which again, if we did 3, 2, 7, 6, 8 to the power of approximately, we get approximately 32. Anyways, so that's just introducing you to the next level of root stuff, where instead of just square roots, we have also cubed roots, and any root really. Like fifth root would mean what number times itself 5 times gives you a number. So yeah, that's what rational exponents and zero and negative exponents and rational exponents mean. So practice works there for you. Hopefully it works for you. If not, of course, let me know. Ask some questions. Just email me or post in the discussion help thing. If you just put a question in the submission file, that's probably not the best way, because I don't necessarily see those right away. Right? I make sure to look at the email and the discussion post each morning, so you get help within 24 hours. Okay? All right. Thanks for watching. Don't forget to like and subscribe. Just kidding. I don't normally say that, but if you want to, as well. Anyways, thanks for watching. See you later.